We know from classical mechanics and relativity that material bodies, and even light, are affected by gravity. For instance, a ball moving upward in a gravitational field will lose its velocity and kinetic energy, the latter being transformed into gravitational potential energy. Likewise, the energy of a light photon emitted in a gravitational field will diminish while the light moves away from the source of the field. Since, according to the famous Planck-Einstein relation, the photon frequency is proportional to its energy, light becomes redder when climbing up a gravitational field. That is known as gravitational redshift. Both these results can be derived by applying the conservation of total energy, starting from slightly different initial assumptions. In particular, using the principle of conservation of mechanical energy presented in introductory physics courses, one can easily calculate the minimum energy required for a body of mass m, placed at the bottom of a pit of depth h, to rise out of that pit. The intriguing feature of the energy conservation principle is that we do not really need to know much about the shape of the pit or the way the energy is yielded to the body. That energy can be defined as escape energy and is reminiscent of, and analogous to, the escape velocity in astronomy and celestial mechanics. Therefore, the energy conservation principle sets strict limits to material bodies in light, in their motion in a gravitational field. However, in our paper, we show that the same conservation principle surprisingly does not pose any limit to the height reachable by a sound wave, in a vertical column of ideal fluid in the same uniform gravitational field. In the paper, we provide two accessible proofs of that counterintuitive result that can represent an amusing digression from the usual presentation of the topic. Moreover, owing to the inevitable association with what happens to light in a gravitational field, we hope that the content of the paper may start thought-provoking discussions among students. We can only spoil that although black holes seem to exist, there are no such things as static dumbholes.